Hello everyone. Uh, Today we're going to present our paper, the VMFormer end-to-end video mapping with transformer. Video mapping is a long-standing task in the computer vision community that giving some video frames that this task aims to give the alphabet prediction of each frame. And it has wild applications like video conferencing and video editing, which needs to output the high quality and time-consistent alphabets from the videos. And current solutions are all based on the CNNs, and the CNN-based solutions have limitations because CNN itself has the limited receptive field. And compared to the attention operator, which can build the non-local connections between pixels, which motivates us to develop a transformer-based solution for the video mapping. And at the same time, in the vision community, there are many works that apply the transformer architecture, which was proposed for the machine translation in the NLP field. And researchers in the vision community have applied this method into the image classification task and proposed the VIT architecture. And also they further applied the vision transformer to some downstream tasks like object detection and segmentation. Like they proposed the data for the object detection that use CNN and transformer encoder to extract image features, and use the queries to make predictions of bounding box. And also some works like sequence former applied the same architecture to the video instance segmentation task that they also use the backbone and transformer encoder to extract the image features, and then they use the queries to make the instance related predictions. And motivated by these works, we propose this VMFormer that used a vision transformer to solve the tree-map-free video instance mapping task. And also we build the both short-range and long-range temporal modeling upon this VMFormer model, and it outperforms previous CNN-based tree-map-free video mapping methods. And here's a overall architecture of the VMFormer framework that gives some video frames. It goes through the backbone and transformer encoder and become a flattened image features. And then we use a set of queries to make predictions. And we build the temporal modeling both upon the features and the queries. And then we just multiply the queries with the features and give the alphabet predictions. And here is a detailed architecture of the whole framework. As you can see that the backbone transformer encoder extracts the input video frames to image features, and then during the decoder part, they do the cross attention between the filters and the queries so that the query can learn the ahead of representation from its features. And then for the for the temporal modeling on the features, we just use the feature map cross frames and use some combination of the convolutional neural network and the recurrent neural network to augment the features. And for the long range temporal modeling, that we just apply a simple linear layer to learn some temporal weights upon the queries, and then reweighted all the queries. And then during prediction, we just multiply this reweighted queries and also the new feature pyramid, and give the predictions of the alphabet. And here are some experiments of how we set up the baseline. That there are many hyperparameters like the number of encoder and decoders, or the loss ratios for the focal loss, or like how many supervision we should be used on the prediction, and how long we should train the framework, because the transformer-based solutions are new to this field, so all the training settings should be evaluated. And then after building the baseline, we mainly did an application study on the short-range temporal modeling and the long-range temporal modeling on the queries. And upon this strong baseline, we can see that the temporal modeling can still make a significant performance improvement over this strong baseline. And then we compare the VMFormer to other state-of-the-art CNN-based solutions. We found that both in the low resolution input and the high resolution input, the VMFormer can outperform this CNN-based methods. But also, it also has still have some room to improvement on the temporal consistency. We further do some zero-shot evaluation on VMFormer on some other video mapping benchmarks. We found that the model can also do a good job here. And we also evaluated the speed of this VMFormer solution because for video mapping task, many scenarios require real-time inference. And we see that VMFormer can also reach the real-time inference with the low resolution data. And we also did some visualizations and compared with VMFormer with other models, and they show that VMFormer can have some good predictions on some challenging scenario. So here comes to the conclusion that we propose VMFormer, the first end-to-end treatment-free video mapping method that based on a vision transformer. We also build some short-range and long-range temporal modeling upon the model and make the model outperforms the CNN-based methods. And we hope there are more works about exploring vision transformer applications on the video mapping task. Yeah, thank you.